Hi everyone. In this video I'm hoping to explain to you the different number systems, binary, decimal and hexadecimal, but all you need to know is that they are all just numbers. What do I mean by just numbers? Well, binary, decimal and hexadecimal are just mathematical notations representing numbers. So numbers are absolute. The way we represent numbers can vary, so that's the numbering system that we use. So that sounds a bit confusing. Well, in English we count using 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. This is decimal or base 10 number system because there are 10 digits. Okay. In binary, which is what computers use and is a base 2 number system, there are 2 digits to count with, 0 and 1. Okay, and in hexadecimal, which is base 16, there are 16 digits to count with. So because we're doing this in English to represent these 16 digits, we count 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we need another one, so we just go A, B, C, D, E, F. So we can count with characters from 1 through 9 and A through F. So in this case, A represents what we know as 10, B represents what we know as 11, C represents what we know as 12, D is 13, E is 14 and F is 15. Okay? So we're not actually counting with letters, we're just using letters to represent numbers. How? Well, this is about to get a little bit complicated. Since there are 10 numerical digits in decimal, which is also base 10, when we count beyond 9, we need to add an extra digit. In this case we count to 10, which is a 2-digit number. So we'll count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What now? We add an extra number. So now we're up to 10. This is just a 1 and a 0. This is a 2-digit number using 2 digits from our base 10 number system. So now we have 2 digits, which is why we need to look at digit spaces or digit placing. Okay, so we've got the first digit and the second digit, and let's look at a 3-digit number. So a 3-digit decimal number, in this case we'll use 482 as an example. The leftmost character in this example is multiplied by 10, which is the base value because we're using base 10, to the power of 2, which is the same as 100. So in this case it's the leftmost character is multiplied by 100. So that's why we say 400. So when we look at a 3-digit binary number, 010, the leftmost character is multiplied by the base number, which is 2, to the power of 2, which is the same as 4. In hexadecimal, base 16, and as you can see there's a letter in this number, the leftmost character is multiplied by the base number, which is 16, to the power of 2 again, which is also the same as 256. Are you starting to see the pattern? The base number is the number before the power by which that particular character is multiplied. I know this is confusing, hopefully we'll simplify it over the next few slides. The base value of a number is used to calculate the value of a number in a digit placing. Bit confusing. So how do we calculate these crazy numbers? Well, the first digit is a portion of the base value. So in base 10, the first digit represents a portion of 10. So what I'm saying is 1 isn't 10. 1 is a tenth of 10, obviously. The second digit is a multiplication of a base value. So in base 10, the second digit represents a quantity of 10. So 20 is 2 times 10. Obvious again. In subsequent digits, they're a power of a base value. So in base 10, the third digit represents a power of 10 to the digit placing. So 100 is 10 to the power of 2, and 1000 is 10 to the power of 3. Okay? So let's look at some of these digit places. The first digit, a little bit counterintuitively, is on the right hand side. Now we read left to right, but with numbers the smallest number is on the right, and then we add numbers to the left as the number gets bigger. So the digit spacings here are represented by, or the digit placings are represented by first, second, third, fourth and fifth. We know these traditionally to be 1, 10, 100, 1,000, 10,000, but really all they are is this number multiplied by the base value to the power of this digit placing. So with each digit placing, the power value increases by 1. Okay? Here's an example. In base 10, where base equals 10, the number 73,284 is 7 multiplied the base number to the power of 4, so that's 7 multiplied by 10 to the power of 4, plus 3 multiplied by 10 to the power of 3, plus 2 multiplied by 10 to the power of 2, plus 8 multiplied by 10 to the power of 1, plus 4 multiplied by 10 to the power of 0. This very basically is 70,000 plus 3,000 plus 200 plus 80 plus 4, which is the number 73,284. In binary, which is base 2, the number 10101, or what we know is 10,101, which isn't the way we would say it in binary, is 1 multiplied by the base number to the power of 4, so that's 1 multiplied by 2 to the power of 4, plus 0 multiplied by 2 to the power of 3, plus 1 multiplied by 2 to the power of 2, plus 0 multiplied by 2 to the power of 1, plus 1 multiplied by 2 to the power of 0. This is also just 16 plus 0 plus 4 plus 0 plus 1, or 21. Normally when you count in decimal or base 10, you stop when you get to the 10th character, and then you go into double digits. This is because there are only 10 characters. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. In base 2, you only have 2 characters to count with, so you go into double digits very quickly. In base 16, you have 16 characters to count with, so you can count higher with fewer digits. In this counting example, the representation of a number, 101, in each system means in decimal it's 101, in binary it's 5, and in hexadecimal it's 257. So why do we use hexadecimal? Well, computers count in base 2 or binary because electricity can only take 2 states, either on or off. So that's only 2 digits that computers can count with, either on or off. It's more efficient to count with 16 characters on a computer than counting with 10. So why is it more efficient to use hexadecimal numbers when we're dealing with computers? Well, if we were to write a long string of characters, in this case we were counting in decimal, the decimal number 9 is represented with 4 binary digits. 9 is 1010. The hexadecimal character F, which is a decimal 16 in binary, is 1111, which is also 4 digits. So when we start representing large numbers using decimal numbering systems, we lose digits. There's useless digits in there. We're not using binary to its full capacity because the highest number we can go to is 1010, which isn't the highest that we can count with 4 binary digits. Whereas hexadecimal uses all 4 digits in that sequence to reach the highest possible number. And wasting digits means wasting speed, so we want to make as efficient use of binary digits as possible.